Hi again. In the very last thing that we want to do for this overall review of Module 3, we will be going through a simple example that involves certain aspects of the phenomena related to surface tension, and also certain other aspects of other topics that we have covered in Module 3. This is a relatively simple example, but it captures the most essential parts of skills and strategies that you may need to have in the final exam for Module 3. What we have is a nozzle that is kept perpendicular to a disk object, and through the nozzle, through the orifice or the opening of the nozzle, there's a liquid jet with a diameter 2 times Rj. Rj is the radius of the jet that is coming out, and vertically is coming down, and it impacts upon this disk-like object or disk-like target. The disk-like target is just a solid target. It's a small and it's axisymmetric. It's placed exactly at the center of the jet, so the problem will have an inherent axisymmetry embedded in it. That may help us because we can easily choose a cylindrical coordinate system, r, z, and theta, as shown here. As the jet impacts this disk, it will form a very thin disk of liquid. For example, if it's water, it will form a very thin disk of water. You can do this very simply at home in the kitchen. Open the tap of water, put a spoon or something relatively smooth under it, and you see that a very thin sheet of liquid, which looks like almost a thin disk, expands radially outward. This thin disk of water or sheet of water that is expanding radially outward will not continue to infinity. We will see that at a certain point, at a certain radius captured by the big R here, it will stop expanding, and it will actually form small droplets that fall down from the rim of this disk. The rim of this disk, if you look at images that we will show to you, or if you do the experiment yourself, is a relatively thicker rim. It's a torus-like structure that is sitting at the very outer edge of this expanding sheet or disk. When the problem is a steady state, we notice that the whole process looks like it's stationary, other than the fact that there are droplets that continuously leave the rim and fall down. But the radius of this disk remains constant. Question of interest is what sets the radius of this jet. So we want to address that. The very first thing we can do, as we have learned in many of these problems, is to just choose a suitable or acceptable contour volume and think about forces and flux of momentum coming in and out of that contour volume, or forces acting on the contour volume. The contour volume I have chosen is shown with this dashed green line here. It's basically a zoomed view of the very edge of this water sheet. When I look at the very edge, I notice that there is definitely some incoming momentum from the left-hand side that's captured by velocity at the edge, which is v at position r equal to capital R. And I also notice that probably this sheet has a certain thickness, which is captured by the height of the sheet h at position R. So again, this is the very end of this disk, so it's almost at the radial position R equal to capital R. That's where we are looking at the problem. And we can easily write down at least or draw the forces that are acting on this contour volume from outside the world. There's gravity, of course, but in this problem, more than vertical balance of momentum, we are interested in the radial balance of momentum because we are thinking about finding a radius. Whenever we cut an interface between water and air, there's a line force acting on that interface. That's what we learned in the surface tension section. So we need to draw that line force, which I'm doing with this magenta color. And we call that F sigma, F sub sigma, which is the surface tension force. This surface tension force is nothing other than the constant of capillarity, which is surface tension between water and air, which is 72 times 10 to the power of minus 3 Newton over meter. And since it's a force per unit line, to get a force out of it, I need to multiply to a unit of length. The contour volume that I've chosen is going into the board. It's basically rotating. This is the cross section of it, is rotating into the board. And I can easily take just a small unit of width of that, which I call W. And W, by definition, is nothing other than a small section of this problem as it goes into the board that has a length r d theta. So if I have this force acting on it, I may ask also, what about momentum that is coming into the system? So the momentum that is coming to the system, which I show it as momentum coming in, is nothing other than density of the liquid, rho, multiplied to the velocity at this position, which is r equal to r, v squared times density, rho v squared. That's the momentum flux that I have. I should multiply it to an area, and the area again would be the unit length that we are going into the board, which is W, and the height of this, which is h at position r. So again, you need to remind yourself this W is exactly the same W that we had on the top, which is r multiplied to d theta. Now that I have forces acting on the contour volume and momentum that is entering it, I can think about momentum exiting it. Again, I can think about momentum of the droplets exiting, but if I notice the droplets are vertically falling down, they are not giving me any x momentum. So if I only consider balance of momentum in the x direction, I will be only dealing with this force and with this momentum coming in. So this is all I need for balance of momentum in the x direction. There is certain amount of momentum that leaves the contour volume as these droplets fall vertically, but that's purely vertical or y component, or actually I should say z component, because we are using r theta z. That's purely z component of momentum. There's no r component of momentum, or here in this, rather than x, I should have used r. There's no r component. And you can think of, if you like to think about an equivalent x and y, x in this direction, horizontal, and y vertical, is equivalent to the same thing as r theta, r and z. So this is r moment. So let's write down the conservation of momentum in the radial direction and see what we get. The conservation of momentum will give me the following. First thing that I have is the forces that are acting on the contour volume. So I have 2 f of sigma, so 2 times f of sigma, which is sigma multiplied to w. So that's the net force that I have. And this should be equal to the momentum. This completely cancels the momentum that is coming in. So the momentum that is coming in, which I will show with the blue color in a moment, is equal to rho v squared, and this is velocity at r equal to r, multiplied to w, multiplied to height at position r. If I cancel things, for example, I can easily cancel w from this side with the w that I have from the other side. I can easily show that the balance would give me that 2 sigma, and I may continue actually with the white color here. I can get the balance that 2 sigma, which is surface tension, divided by, on the other hand, h at position r remains there, so I bring it to the left-hand side, would be equal to rho multiplied to v squared at r equal to r. So a very simple balance of force already gave us something very interesting, which is a relationship between the incoming momentum and a certain type of capillary stress that is resisting it. This is the pressure, the dynamic pressure that corresponds to the incoming momentum of fluid elements that enter the very edge of the liquid sheet. And this is the capillary pressure that is actually acting against it and is holding it. So really the balance of this liquid sheet is nothing other than inertia wanting to expand it further and further, and capillary putting a brake on it and holding that inertia at a certain equilibrium radial distance r. We have this relationship. We can actually think of this can be the solution, but you see that there is something unknown. If we really want to find the radial position for the sheet, capital R, we need to really talk about how h as a function of r and how velocity as a function of r vary in this problem. For that, we will need a little bit more information about the fluid phenomena in this problem, and that's what we will do in the next video.